Matlab on.
All right, I turn on the recording now. It is recording. So let's do some MATLAB again. And then finish up that MATLAB. By the way, the homework due is the next class. Um, and also I posted the class notes for mechanical system. I used to write this on the whiteboard, but now because the time is limited and I don't want to compensate since this class is virtual, I want to use this and do even better than regular semester because we are saving sometimes in places. So I put this is this was written by Jose Hurtado in two years ago, and it is very similar to, I mean, I would follow the same line. It is what I wanted to say. So you don't have to write it, but open it up. Then I'm going over it and we go over it together, and it saves a lot of time. But I prefer that you follow the class because when you're writing and you're present in the class, you can't think about something else. But in this online setting, you can. And I mean, this is the nature of human. So let's first do the MATLAB and do some more practice in MATLAB. Everybody open MATLAB and let's do this while all of you are doing this. You know what, let me share screen, maybe the whole screen, because when we have different plots and stuff. Okay, now let's say we wanna plot something which is a little bit more complex. I mean, plot a Fourier series of a square wave. So first, let's see what is a Fourier series of a square wave. Google it. And the first link, I mean, Wolfram MathWord, this is a good link.
But it be raining out there.
Yeah, it is. What? Are you talking to me? Let me.
Oh, sorry.
But it is also raining like crazy outside now in Oxford. Okay, so look at this Fourier series. We have this square wave. The Fourier series is insanely important because let's say you are, for example, talking and you want to send over the signal to some other place, let's say through communication, right? Voice communication. Then if you look at the frequency content of a human voice, you will see that you don't have anything above 25 kilohertz, nothing. So all of that is noise. So so you can filter it out and save energy and data to send over, because anything that was above 25 kilohertz was not your voice, it was noise. So filtering and looking at the frequency content is really useful. Now let's see what is the frequency content of a square wave. It is in fact infinity. It has all the frequencies. What do I mean by that? I have to add different sine waves. This is a big square. This is, I mean, the biggest sine wave. And then one sine wave, which is like that. If I add it to this red one, add that small one with higher frequency to this red one, it becomes this blue one or yellow one. Let's say I have this one. So it becomes that yellow one. And then when I add more and more and more frequencies, you see it resembles that square wave and it gets closer and closer. So we want to graph this and we want to make sure that, okay, this is true. So we want to first graph the square wave. How should we graph the square wave? You see, it is from 0. Let's say instead of L, I put 2. Just for the sake of simplicity, I put 2. So from 0 to L over 2, which is 1. From 0 to 1, it is 1. And then from 1 to 2, it is -1. You see 1 and -1. So I want to graph that line, 1 and -1. What should I do? I mean, how I can say that, okay, well, first of all, I should define x. X goes from 0 to 2, right? The x, I mean, the x goes from 0 to 2, and then we have to say that, okay, when x is less than 1, the y, or f of x, y should be 1. If it is in this range, it should be -1. So first, let's start that. This is from previous. Okay, remember I said that it is not a bad practice, or in fact, it is a good practice to always put clear at the beginning. If you don't need anything from previous code. If you do, it would be, I mean, not wise to put it there. If I were not recording myself, I would say it would be stupid, but now I should say that it is not wise. All right, so clear, and then x, I'm sure that this one I know, x goes from 0 to 2, right? But remember a semicolon, so I shouldn't speed out that. But remember, if I put that, it would be 0, 1, 2, and not many points. So what should I do? I say that, okay, the resolution is go above, go with 0.01. So I have 201 points now, because it goes from 0, 0.01, 0.02, 0.03, all the way to 2. So because I start from 0, it would be 201. Okay, now I want to define y. How can I do that? I should say y if this is how can I do that? I want to make sure that I have to go one way, which is not the fastest way, but it is the, first way that comes to mind is that let's check every x. Every x, I'll go over all x's. By the way, anytime that you want to see the output, you can highlight that and then right click, and it says evaluate selection. So it just ran that part. You see, it ran that part and it spit out all the numbers because I didn't highlight the semicolon. I intentionally wanted to see the numbers. Okay, so if I go one by one and check each one of them and say that, okay, check this one. If this is that, makes it 1. 1 all the way I go, and until I reach 1. And I said, oh, now I reached that point. So from now on, make it -1. So check that, check that, check that, check that. All right. So in order to go one by one, I use a loop, right? So how can I use loop? In Matlab, it is for and end. I use for and end. For I put a dummy index. Because this, I want to go I equals 1, 2, 3, whatever. 1, 2, I said I have 201 points. In order to check all of them, I have 201 points. Look at this here. X equals to, by the way, I still have Y from previously. Let's make it clear. And then run it again. Highlight all the way this time. Evaluate selection. You see, X is 201. But probably, this is one way to do it. I look at the X, what is the size, and I might do a mistake. And next time I want to make it to 3. And I have to change all these, right? This one as well. So why not, instead of 1 to 201, look at the size of X. So what is the size of X? How I can do that? You can Google it. You can see size. You see, size of X. It gives me 1 and 201. Why? Because this is number of rows and this is number of columns. And in fact, you see that here, 1 by 201. One other way when you're dealing with just a vector is length. It is easier because if I use size, I should say, okay, pick the second column. But if I just use length, it gives me that thing. So instead of saying go to 201, I say go to length of x. Anybody has question?
I had a quick question, but it deals more of like submitting homework than the actual content we're going over right now.
Okay, what is that question?
Since most of our homework, like the answer's gonna be on Matlab, how do you want us to submit it through Blackboard?
I open up something that you upload. I mean, there is a way to, I mean, anybody can upload in their own section. So you will upload it. But this was discussed in the last class a little bit. You copy and paste, make a one Word file, copy paste the code. I mean, screenshot of the output, copy paste that figure in the Word, everything in one single Word, and then print to PDF. Because Word, I mean, if you have Microsoft Word, which is after 2000 or something, you can always print to PDF. So at the end, you would have the code, output, and whatever you write up, you want to write. Even you can write by hand and then take a picture and then upload it into that Word if you're not, I mean, comfortable with typing. So in any case, just one PDF file.
All right, thank you.
No problem. So, okay, let's say for I equals to 1 to length of x, and then I should use that if statement. If x of I, because you see, I is the one that I'm going over the loop. I mean, I equals to 1. Next time that I come back here, the code come back here, I equals to 2, I equals to 3. So x of I means that x1, x2, x3, x4. I go over all of the x all the way to 201. So if this less than or equal to 1, then whatever you put after if, the next line, it would be like do this, okay? Y of I equals to 1. I define this time Y. Okay, now I would say, I want to say that there are, I want to check that if it is other way. So I would say else if x of I bigger than 1, just to make sure, I want to say and it is smaller than 2, right? I don't want to pass 2. And in Matlab, you use second and. I mean, and sign second, because we are using the, let me see, maybe it is changing and because it is, okay, and x of I is smaller or equal to 2, then y of I equals to -1, semicolon, right? Now I have to close this for loop because you see it says that an end is needed. And I have to use this, I have to close this if statement. Again, you see if I hover over that, it says that end is needed. So I put one end, enter, another end, enter. And you see there is a Matlab shows that, okay, these whole lines, that's why you have more space, more indent, that, okay, this is all of these lines are inside this loop. If you, I mean, have it like that, it wouldn't be any problem in terms of syntax. At least it wasn't. I'm not sure now, but let's say. I don't think that there is any problem with that. It gives you warning, but it won't be any problem. Let's run it. It just ran, and you have y. Let's plot y versus x. X, so I put x and y. I don't know why sometimes my plot doesn't show any figure. And I have to run it second time. You see, it is 1, and then it goes to -1. I can change the limit so you see that line, because this line is embedded there. But if I hover it, you will see that there is a line over there. Okay, it is 1, and it is -1 from 1 to 2. All right, so it would be fine now. Now, by the way, I mean, if I have it like that, if I highlight all of them and then right click, and you see smart indent, it makes it like before. It is easier to read this code, obviously, because you see that, okay, this whole thing is within that loop, and this whole thing is Joe's condition for that. You can make it faster. You can also say that else yi equals to -1. Why? Because it is either smaller than 1 or else it is bigger than 1. It means that it is bigger than 1. So you put it there. And there is a faster way to do that as well. I mean, without this loop, but I don't want to go over that. But let's say you're plotting that. So let's put line width. By the way, this is line width. How do I know that it should be line width? Because I read the help. So it would be 5. It means that make it that line a little bit thicker. Now let's look at this is y itself, the function. Now we want to draw that Fourier transform, right? So yf, I call it yf equals to, look at this Fourier transform. It is 4 over pi. Let's make it smaller, and I see that. Let's first pick up to the 7th element. You see, m equals 1, 3, 5, 7. It is just odd numbers. 4 over pi. And I have to add all these, right? All the way to infinity. But I want to go up to the 7th element. 1, 3, 5, 7. So I should have 1 over 1 sine of 1 pi x. And I said L equals to 2, right? I said L equals to 2. Assume L equals to 2. L is the whole period. No, L equals to 1. Because this is L1. So we go all the way to 2. So L equals to 1. Okay, so I should put 4 over pi. I want to go all the way to the 7th. 4 over pi. By the way, pi in Matlab, you can just type pi multiplied by this whole thing. I mean, I add some of the stuff. So let's put a space between parentheses so I can see easier. Sine of pi times x plus, I can put space just for the sake of, I mean, visual, 1/3 multiply. Don't forget, sometimes you forget to put multiply because in writing, we don't have that multiply, but in fact, Matlab needs that, right? Sine of 3 pi times x dy, okay, that's it, plus 1/5 now, because I'm lazy, I can copy paste. I know that I should just change the 3 to 5 and 7. Okay, this should be 5, 5, 7, 7. Now you see, if you highlight the parentheses, you see that this parenthesis is corresponding to that one. So it is not balanced yet. Why? Because of this one. So I have to close that thing. You see, when I put that parenthesis, is highlight the parenthesis that it is corresponding to. So it means that it is balanced, and still I have a warning because I didn't put semicolon. So now I have YF. right? So let's plot this along this plot. So I put hold on because otherwise it would put this on top of that. Then instead of that, I would say YF, right? So I mean, I'm plotting Y and
Dr.
YF.
Farshbud,
Yeah,
why did you do the hold on again?
because if I don't have this hold on, let's just comment that out. It plots this one, and then when it reads that one, it plots this one, erase the previous one. Let's see, you see, I just have this one without hold on, but with hold on, it keeps the previous plot, that blue one, and it draws the second one on top of that. So you see, I'm plotting, and you see it is resembling the square wave when I go up to 7th. What if I want to go up to 51? I mean, a large number. It should be odd number, not 50, because remember, it's, you see it is 1, 3, 5. So let's say 51. So if I want to go up to 51, what should I do? Type all of these?
You can do something similar to what you did for X.
Exactly. I do a loop, right? Why? You see, because it is already, it's like a sigma, and it is given to me in terms of n. So it is easier to do a loop, even for the 7. So I say for this time, I use n, the same thing that it is there. N equals to 1. And I should go above, I mean, instead of go 1 by 1 by 1, I jump just over the even number. So I go over odd numbers only. So this means that 1, 3, 5, because I go above by amount of 2. If I didn't have that, it would be 1, 2, 3, 4, 5, 6, all of them. But I don't want that. I want to go 1, 3, 5, 7, just odd numbers. So YFF equals to, let's put the small one like previously so I can, equals to YFF. I keep whatever I had, I add to that other terms. One way to do this sigma, you see YFF initially is 0. So now the first time I add what? I add 4 over pi multiplied by 1 over n, because you see I have n, and this is my counter. This is first 1, then 3, times sine of n multiplied by pi multiplied by x. And then that's it, end. By the way, I want to suppress the output. So if I didn't have YFF equals YFF, if I didn't have this, each time it would rewrite on top of YFF. So when n was 1, it would be 4 pi sine of pi x. Then when it would be 3, 4 pi, 1 over 3 sine of 3 pi x. It would change, but I don't want that. I want to add them up. I want a sigma. So each time I keep whatever I had previously and add to that the new term, right? Oh. So let's, again, I already hold on to the plot, so I didn't hold off. So let's plot. This time I want to plot YFF, right? Let's see. By the way, line with 5 is too much, probably. I should make it 3 because it is. Okay, let's see how all the way to 51 works. What? I don't see that. Okay, it was an error. Unrecognized function or variable YFF. Because it wanted, do this YFF. This is new in MATLAB. I can
You have to do y of f equals 0.
exactly. Before this loop, I put YFF equals to 0. And that is not, even if it was, I mean, previous versions, it was a better practice because if I run this code twice, it wouldn't add to the previous one that it is already in the memory. Although in this case, I have this clear, but just in case, this is always a good practice to put 0 at the beginning. So because this side, it has to be defined, but previously it was by default, everything was 0. Anyway, so let's, so this is, you see, this is the square wave, which is hidden now. And this is all the way to 7 components, and this is all the way to 50th. You see, it becomes really close to the square wave. There is a difference though, and this is called, I mean, probably if you do too much, you will see that, let's do it to 91. These are some math. You see, the red one was 51. This yellow one is 91. If I zoom in, let's zoom in here. I mean, this has nothing to do with the course, but you see this height is not decreasing. So we have the jump overloop. I mean, over jump of this value. The width of this erroneous, let's say, erroneous jump is getting smaller and smaller and smaller. So it becomes less and less important, but still we have a jump in that value. And this is called Gibbs phenomenon in Fourier transform. So it is easy to see that with MATLAB. All right, any question? This is very similar to one of your homeworks. Okay, let's get back to the okay, everybody go and open up that chapter 2 mechanical system that I posted on the Blackboard. Okay, a mechanical system, there are 3 main components: inertia, stiffness, and energy dissipating. Inertia is mass. It is not just necessarily mass, it can be moments of inertia. For example, if you have a flywheel, the mass is not used for storing energy, but the moment of inertia is used. So that is inertia. The more general term, it's not just mass, it is inertia. Stiffness, I can't say that it is just a spring. It is stiffness in the system. And energy dissipating. This is something that dissipates energy from our system. You might think that, I mean, the name is used, the name sounds like negative. I mean, it dissipates energy. But sometimes it is insanely useful. Anybody can come up with an example that energy dissipation is good?
Dampers.
Dampers. Why dampers are good?
For like car springs, for example. So you can go over a bump, it helps dissipate the energy, helps the ride better.
Very good answer. If it wasn't for damping, if you would go for a bump, in ideal world, you would, I mean, vibrate forever. Even in non-ideal world, you would vibrate, I mean, the car would go up and down for a while. And assume that you're off-road. You hit the first bump, it goes wide, and then before it settles down, you hit the second one, third one, fourth one, then you will lose your brain if it wasn't for damping, because it would add energy to your system. Each time you go over a bump, it would add energy to your system, and after a while, the energy would be too much. The structure wouldn't tolerate that. right? And there is example for the bridges. If there wasn't for damping, in fact, you can watch on YouTube, there are bridges that they just due to the wind, they collapse. Why? Because it swings, and the frequency of the wind is the same as the natural frequency of the wind. The frequency of the bridge, natural frequency of the bridge is the same as the frequency of the wind. So the bridge absorbs energy more and more, then it would collapse. There, for tall buildings, it would be the same thing. Sometimes when you want to build a tall buildings, you have to have some damping mechanism. There are some very novel damping. You see, for example, if you live in a very high-rise building, in a windy area, you might get seasick because you don't know it, but you're moving very slowly over time. And the seasick is caused by something like that, because your eye would, before, I mean, even if you don't recognize it, your eye is fixed to, for example, far objects, and then your brain is moving, so it can't comprehend that. Anyways, you get seasick. So they add damping sometimes in a very tall buildings, especially if they have a pool at the high level. Anyway, so the name is negative, but it is not negative. It is sometimes really positive, and sometimes it is negative. Or if you have a washing machine, you will, uh, if somebody turns on their washing machine on the third floor, everybody would hear it if there wasn't for damping on the washing machine. What we use in this section is mainly use Newton's law, first, second, and third, and Euler's law of motion to get ordinary differential equation. By the way, Euler's laws of motion, it is based on Newton's law and some math. But Newton's laws, in fact, are not based on math. They are based on experiments. These are the core physics. F equals to ma. It is nothing mathematical. It is mx double dot, but it is proved by experiment, not by math. So this is that core physics that everything else is built upon that in dynamics. And this counterpart of that for electrical system would be Maxwell's law. So this is second law that we used, x double dot. I said in the first class probably that it is a double derivative with respect to time. And the other one, moment equals to I alpha, and I is moment of inertia about the axis of rotation. T is torque, and alpha is angular acceleration. If you compare these two equations, you see force is like torque, mass, the inertia here is like I, moments of inertia, and A is like alpha. So how, you don't have to calculate I in this course. You can use back of the book to see what is the I around axis of rotation, because I is different on different stuff. Let me use whiteboard. No. Okay, now stop that and then share this one. All right, we're talking about I. I depends on the axis of rotation. What do I mean by that? If I have a disk, you have a feeling that it is to some extent difficult to speed that up, right? If the axis of rotation is like that around this point. But if it is, let's say I have something like that very far away attached to that disk, and I want to rotate it around this axis, it would be more moment. So the axis of rotation is important. I mean, you will see that the parallel axis theorem, that it will be m this distance d squared equals I around this. So for I of this, it is 1/2 of mr squared. You can look it up from the back of the book. I'm not sure this book has it, or to be honest, I forgot. But all the dynamics book, they do. No, this doesn't have it. But all the dynamics book, and forget about the book, you can just, Google it, moment of inertia of a disk. And you can calculate this as well. I mean, it would be this, right? The elements of area, it would be this. This would be dr. This would be r d theta. So the mass of this would be the whole mass, which is m, divided by the area, which is pi r squared, times by the area dA, right? Which is m p r squared. And I said that the area would be r dr d theta. So I should just do double integral of this. This is mass, m r squared, so it would be pi r squared, r dr d theta, m, you see, I mean, for a moment, it would be r squared. So if I do this from 0 to pi and 0 to r, I would get the same thing. Why? Because if you do first integration with respect to theta, it would be 2 pi. Pi cancels out. It would be m 2m r squared. Then I would have integral of 0 to r. I got rid of that. It would be r cubed dr. And then this would be 2m r squared. And then this would be r fourth over 4 from 0 to r, which is r squared, r to the power of 4. This is m. R to the power of 4 over 4. 4, one of them goes away, so it would be 1/2 m. 2r goes away. This becomes r4, 1/2 mr squared. So you can calculate this, but this is not the topic of this course. The reason that I went over it, because in my first job interview, before I do my PhD, this light in my room is going up, is going on and off by itself. I should turn it off. Okay, my first job interview, I said it in previous classes. I was asked to do that, and it was for Western Digital. It was before I started my PhD. Anyways, I'm saying that it is not a bad practice to calculate some of them because it has calculus and some dynamics as well. Anyway, you can calculate this moment of inertia, and it depends on the axis of rotation, as we said. Let's get back to that. Okay, now stiffness element can be a translational spring or rotational. In general, force equals to K times X. I mean, X is displacement from the equilibrium position. X is displacement, not the length of the spring. The spring might be unstretched and it might be 2 meters. The force is still 0. If that spring is, stretched, then we have forces. It is a very simple model, but it is not just math curiosity, or it is not just on paper or homework for physics. It is in real life as well. Why? I mean, it embodies a lot of different mechanisms, a lot of different forces. Why it embodies that? Because let's say you have a cantilever beam. Anything that it is fixed at some point, it is like a cantilever beam. Assume that you have a very big column, so yes, you can assume that that is solid, and you have another another horizontal column, and there is some load on that. You want to see how much is the displacement. Well, you can use methods of that you learn in 312, strength of material, or again, look at the I mean, Google it. So you will see that x equals to f L cube over 3EI. We are changing f and see how it changes x. For example, you want to put some load, less load, and x is, L is not changing in your structure. E, which is the I mean, modulus of this beam is not changing. I is not changing. So all these L cube over EI, they are constant. If I write f in terms of x, it would be 3EI over L cube x. But you see the relation between f and x is still linear, and I can call all this stuff just k. By the way, this is the way that most of the electronic scales work. You have a small beam, and when you go on top of that electronic scale, this would deflect, and the deflection is measured by strain gauge, but it is the same principle. That strain, or that, I mean, displacement depends on the force, which is on your weight. So if you want to, I mean, weight less, you can reduce the F by, I mean, exercise or eating less, or you go and live on the moon. In both cases, you would be, and for me, I guess living on the moon is easier than, I mean, exercise. Anyway, so you can have this, I mean, simple model, even in embodying more complex stuff. The same thing for pin beam. This time, x equals to FL cube over 48 EI. But if I just move around coefficients and I see that it is 48 EI over L3, still it is a constant, so I call that K. So F equals to KX. For rotational spring, T equals to K theta. We have torque and we have theta. Anybody can give an example that we use or we need to model torsional spring or rotational spring? Not everybody at the same time. Okay.
Can you repeat the question?
Can you give an example of a rotational spring? A very, I mean, weird example that probably come to mind is those mechanical watches, right? And some of those watches are really expensive. I mean, if you have a skeleton watch that you see all the mechanism inside, some of them are automatic, meaning that you don't have to wind it each time. So, I mean, it has a spring at the end of the day. It has a spring, mechanical spring. But that is a very narrow, but very obvious rotation on the spring. The other one that you need to model a lot of time, and it is very important, is when you have an axle. For example, in a truck, heavy truck, the motor rotates that axle, but because it has some springiness. I mean, you have, let's say you have differential here and you have tires here and motor here, internal combustion. When it rotates, this doesn't act like a solid object. Even a steel, the hardest steel, when it is long enough and the load is hard enough, it has some difference between, for example, this angle and that angle. It has some springiness in it. And you have to model for that, because when you brake, it changes your motor. The other application, when you're in very high speed, where, for example, jet engines, the same axis, you have to model for that springiness in the axis. When it speeds up or slows down, all these, I mean, you have to model, you have to take into account that no axle or no, let's say, beam is solid. If it is really rigid, you can make it big enough to be really rigid for that load, but it is not a wise engineering, and that's not why they pay you, because they want to get away with as less as possible, as cheap as possible, and do the same job. So you can do it with, I mean, you can make it more rigid with thicker or, I mean, larger beam, but you don't want to do that because you can model it and do it with smaller ones. So, I mean, safety factor of 100 is not acceptable for an engineering project. Anyway, let's stop here, and the homework due is next class. I'll post the next set of homework on next class and also the solutions. So you will see, I try to do that today or tomorrow. You will see how, I mean, you can upload the homework, just one single PDF. All right, any question? By the way, read the rest of this material for the next class. I mean, you don't have to read it and understand it thoroughly, but have some idea. And come to the class with questions. That would be the best. All right, see you on Wednesday, everybody.
Thanks, Doc.
Thank you.
Dr. Fosbud,
Yeah.
on Blackboard, where is like the actual like submission tab for the homework? Because when I go to homework, I click on homework and it just sends me to the
No,
PDF.
I haven't made it.
All
yet.
right. You haven't put it up. Gotcha. All right.
Yeah.
Thank you.
No.